grade if you haven't done it yet. It's undergrade either way, but if you have a 0 if you haven't done it, is getting paid for the AP test. Remember, our deadline is next week, and if we don't hit that, then you're going to have $40 extra to pay, which who wants to pay that? Okay, so get your payment in, and then you'll take a screenshot of your receipt or your My School fees, submit it for that assignment online, and that's how I know you got paid. Okay, or that you paid. Once again, everybody should be paying for the test to take it. If there's for some reason you aren't wanting to, come talk to me and I'll convince you otherwise. Because to me, like, if you're going to take an AP class, take the test. Like, why not, right? I remember I took AP late my senior year in college, in high school, and I got to the end of the year and I was like, Mom, I don't know if I should take it. Like, I didn't feel super confident in my abilities. And luckily I have a supportive mom, and she's like, just do it. It doesn't matter, because it really doesn't. Like, if you fail, it doesn't matter. It doesn't go on your transcript as they got a 1. It's just not there, right? They don't know any difference between you taking it and getting a 1 and you not taking it. But in the end, I passed the AP language. And so I was like, sweet, I don't have to take freshman English, which was a blessing to me. Because it's just my brain sounds weird, but like I struggle with English language. So everyone pay for that, get it taken care of. The other big one that we need to be aware of is your test corrections and retakes for Unit 2 are due next Friday. So if you haven't started in that process, I would do so ASAP.
Like me and Annie were both. Yeah, you're welcome. I'm so like,
I accidentally walked past her. Oh my god. What am I coming to? I just see. That's like a. Also, I saw Mrs. Albizo leave the classroom. I was like, oh, I don't have to take any. Shut up. Also, Alex. I realized walking in an early morning seminary that I forgot my AP Chem Gases, which is this. But then my dad came Cowboy. See, no, Ephraim. So, Alex, you see how Ephraim's cowboy hat is like, take it off the boot off. Take it off the boot off. Like, it fits really good. Watch. Watch. I have a cranium of a head.
it's okay, I have to.
It's harder. Well, yeah. I have a massive, either I have a massive skull or a massive brain. Probably skull. You know, if someone said
Okay, restart. Here we go. All right. right, I need everyone to take their boogie boards and put them screen side down in the middle of your table.
Screen side
Okay? Some of you, you're fine, but others of you just get too distracted. I know, they're just so fun.
You don't do it.
I was gone, it was okay, but now I'm just helping you. Okay? Alright, so today we are going to be talking more all about gases. So kind of to connect, I did a demo right at the end. I'm going to repeat it right now. It wasn't done very well, as well as to kind of get our brains going. Okay, so pull out your note packet if it's not out yet.
Get your brain.
I want some.
That's hard to learn.
Somebody to love this so hard.
It was really good. Yeah.
This part of the year, Alex, on the show, is just. I wish it was fun. There's still some people that come in early at tests. Yeah. Yeah.
Like I used to accidentally
The 12 of you guys are so like scary because like you guys like go to the last second for that part because you're like you're getting like off and you run from
I think it's fine.
Wait.
Well, that's chips and chalk.
Line up the night.
We do. It's not as bad as ski.
I would actually cry.
Okay, so what we're looking at today, everybody, is, so last time we learned about the ideal gas law, P equals nRT. We did some calculations with this where we ended last time. Right now, we're going to shift to more conceptual side of understanding how these properties are connected. Okay, so there's one side of being able to calculate it, but then also to understand why is it happening. Why, if the temperature goes up, the pressure does this, or if the volume changes, what does that do? So understand at a molecular level what's going on. Once again, the way I visualize a gas, once again, is a bunch of tiny little bouncy balls bouncing around in this balloon constantly, right? That is what gases are and what they do. That's what causes the pressure, right? Because pressure is about collisions and amount. So the more often they hit and the harder they hit, the higher the pressure is going to be. Okay? Volume, once again, refers to the space it's occupying, so the entire volume of the balloon. And then temperature refers to the speed of the molecules. Okay? So the first connection, so let's review this, and if you didn't write it down last time in a rush, write it now. We're going to kind of this middle one first. Okay? So this connection between volume and temperature. So we're ignoring all the other ones, and we just want to look at those two things. Okay? So, if I have this, and now we could do this mathematically too, and I'll show you that in a minute. But conceptually speaking, if the temperature is going to decrease, I'm going to cool the gas down. Don't say it out loud, but fill in the blank on your notes. What's going to happen to the volume of my balloon? Okay, so if the temperature decreases, is the volume going to decrease, or is the volume going to increase, or stay the same? Those are your three choices. Okay, so put that on your notes really quick, if it wasn't already there. Now, whisper to the rest of your table what you picked.
Decreased temperature results in your palm. So big volume. You know what my favorite thing to listen to?
Okay, are we ready to test it? Okay, so I'm going to pour liquid nitrogen. So this is the method I'm using to cool it, because liquid nitrogen is really, really cold. And so I'm going to add liquid nitrogen to cool the gas inside the balloon. Okay, and we'll see what happens to the volume. Okay? So, first off, what is the sound you're hearing that the liquid nitrogen is doing?
It's gonna blow up.
So our liquid nitrogen is boiling right now very quickly, is it going to burn me if I touch it?
No.
No, it's going to freeze me, right?
I volunteer as tribute. Well, it hurts.
No, because it boils and vapor.
So keep in mind, this is a great reminder that boiling is not about hot being hot, right? Boiling is just about a phase change.
And then you just.
And in this case, nitrogen phase changes at negative 200 and something degrees, right? I'll pull it up in a second. I just have to tilt it so we can get, there's nitrogen in the corner of my container.
It's so crunchy. Like a,
Look, it's still liquid.
Holy crap.
Still liquid.
oh, I say we break it.
So what has happened to our volume?
It froze a
What?
lot.
So as temperature goes down, what does volume do?
Go down.
I think we need to grab the tape measure.
But as temperature goes up, what happens to volume? Huh?
What the heck?
It's back to normal.
It's expanding again.
Oh.
Wait, hang on.
So it cooled so much that we condensed like the air inside of it.
They do.
And then
Okay.
it's back. Okay? The best way to pack balloons, because you can literally make them flat and you can stack like hundreds of them together, and then they blow up on their own. Very expensive way to do it, but kind of cool. Yes, Bryson?
So if you did this with a helium balloon, would it not float if you poured the liquid nitrogen on it? Or how would that work with a helium balloon?
Yeah, so it wouldn't, so when all the gas condensed, right, so the molecules inside of here are slowing down, coming together, hence the reason why the volume shrunk so much, right? It's because they're not bouncing around like they were. So same thing, it wouldn't float while it's flat, because they're not moving and they don't have density difference. But then once it warms back up, they're floating.
So wait, would you see like as Porter commented on this, but would you like see like as like it got hotter and like the temperature rose back again, you like slowly like see it just like rise back up? Oh, that was so good.
Sometimes it does. Sometimes the latex pinches in on itself when it freezes. So sometimes they do get holes in them when they blow back up. But otherwise it works out. So, make sense? Logical thing, like it's cool, but like if you visualize the bouncy balls, it should hopefully feel like, oh yeah, that's logical of what's going on, right?
And you die.
Okay. Let's write the equation that goes along with this, and then we'll do our next demo.
So and so says like, you know, kind of like. Shit's easier to
Okay, so with our equation of PV equals nRT, okay, this is on our formula sheet, right? We have this to use, we don't have to memorize it. You can though change this equation in a lot of different ways depending on what variables you're focused on to see a before and an after relationship, okay? So in our equation here, P is pressure, V is volume, N is moles. What's R?
Constant?
The constant, right? It's a constant value. It has a different number depending on what units, but it doesn't change. So what's cool about this idea with the constant is if I rearrange this for R, so I'm going to get R by itself. Okay, so if I rearrange this, I'll get PV over
And R?
R.
You're finding R.
You want to get rid of R.
Oh.
NT, it will equal R.
Wow.
Right? But R is a set value. So because of this idea where all these variables in this relationship will always equal this constant, you can create a before and after equation. Like our balloon was saying, hey, this is the volume before, this is the temperature before. If I change the temperature, we could mathematically calculate the new volume because of this relationship. So the way you do that, so keep in mind, this is on your formula sheet, this is not. And the next equations I write are also not. But see in a sense how you can get there from this. So you keep it related to the constant, then take away the variables you're not considering. So in our example, what were the two variables we were focused on? So I'm focused on volume and temperature. I'm going to ignore the other ones, and now this is my equation. So my equation here is
V over T.
V1 over T1 should always equal V2 over T2. In a sense, 1 and 2 represent like the before and the after. So balloon before, balloon after, they should equal each other because it's a ratio. They're related to each other by that. Okay, questions of how I went from here to here? Because this isn't on your formula sheet. Yeah,
So yeah, just clarifying. So we're finding the volume like it was like normal temperature, the volume, and the temperature being that normal. The ratio is the same as the volume and the temperature.
Exactly. Yep. It's as one goes down, the other must be going down by the same amount.
Okay.
So yeah.
Awesome.
Other questions on that? Okay, and we'll do a mathematical problem in a second with these separate. Let's come to this one. Don't talk to your neighbors. I want you to make a prediction on your own, and then I'll let you compare. So now we're going to do a pressure to volume. So if I decrease the pressure of a system, what will happen to the volume? Now keep in mind, we're going to do a balloon again. Because in order to talk about volume changes, you have to have something that can change volume. Right? Like if you have a beaker, volume can't change. It just shatters if you try to change it too much. Right? So in order for volume to change, it has to be a flexible container. Right? So we're talking about balloons. So if I lower the pressure of the balloon, okay, what can happen to the volume? Okay, all right. Write your answer on the line, and then in a second I'll have you share with me. I'm so sorry.
This is how these know.
Well, I wasn't expecting that. That's the balloon.
No, I didn't see. I got these pipe cleaners. What else? I hate popping balloons.
Another back.
Okay. Everyone have their prediction? Okay. All right, so to test this, we're going to use a vacuum chamber, because that's how we can change the pressure. Otherwise, the pressure in the room is just always the pressure. Okay. So right now, here's my original volume. Okay. So observe the size of our balloon. Okay. So we're in change. But we're gonna change the pressure outside of the balloon. Yes. So I'm gonna put this in a vacuum chamber and lower the pressure, meaning I'm pulling air out, and it's a vacuum. Right, so I'm gonna suck the air out, which removes the pressure from the outside of the balloon. If you need to change your logic, you can change it right now. If you looked at it maybe the right way, but just backwards. Okay, so what's going to happen to our balloon as I remove the pressure on the outside? Okay?
Increasing pressure.
All right, you ready?
Oh yeah.
Open up our tube here. Okay, can you see that over there in that corner? All right, 3, 2, 1.
It's a fancy machine.
It's not instant because we got to obviously like suck the air out, right? Things over here.
Gino, you're just like my clarification buddy.
It's the little guy.
Just like I explain it in my own words. Yeah, they're pushing out more than pushing in.
Hold on, I think I have something not sealed.
The molecule I don't think it's that big.
Let me check all of my ceilings to make sure
Write
that
that on
there's
the
no
guys.
If you decrease the pressure, how much more the little guys pushing out?
Oh,
You forgot to This is how we know. So you're sucking the pressure out of here?
Yep.
We're gonna die!
Oh, shoot!
Just prepare for your air mass drop.
So she's just like looping.
That makes a lot of sense.
Oh wait, yeah.
Okay,
She's like putting it in a hoop.
We're all like,
It's true, it's just looping.
Oh.
It got a little fat. I want it to explode. Oh.
aww. Why do you have to
It's
shrink?
not fat.
Well, it's not. It didn't shrink. It just moved up.
Okay, so what happened with our volume?
It got bigger. More.
Yeah, so volume went up as the pressure around it went down. Now someone give us at a molecular view, talking about our bouncy balls, why is that happening?
Because there's less pressing on
Because
it.
there's less stuff pushing on it, it has more space to bounce around. So it's
Yeah, right? Like right now the air is pushing on it. But if you take away what's pushing on the outside, then the molecules inside are just like, okay, like, well, this is what happens to the human body in outer space.
So that's why the correct price is flat, because obviously it'll be awesome. That's why not like
You have a big enough container with very little size that they can like
obviously like
I'm trying to think of like all astronauts I've ever seen. You know, like they have their helmets. What? With like an actual.
Oh, that? No, I meant. Very much.
It looks the same.
No, there's not a thing outside.
yeah, I'm gonna write it after.
Has anyone tested? Yeah.
That
Like
was
yeah.
Dude, that eagle exactly.
Same thing. If the gas molecules inside. I'm not gonna.
Yeah, why did you dress?
I literally want to
Okay, over here, everybody. So are we focused on now? We're looking at P and P. So everything else goes away. And our equation is P1 V1 equals P2. Alright, so you just get rid of the variables you're not focused on and keep the ones you are. This is what we would call an indirect relationship. As one goes up, the other goes down in order for it to equal. This is a direct relationship because as one decreases, the other's going to decrease too. So direct versus indirect. Okay? Alright, last one, moles versus volume. So this is the idea of if I increase the moles, what's going to happen to the volume. So make a prediction here in the next 30 seconds. Write that in that blank and then tell me what you predict. Okay, so if I add more moles to my balloon, what's going to happen to my balloon?
Well, I mean, it depends on what volume. Like a little bit of like a balloon, but then you add it, it's still it would not
Okay, show me by pointing in a direction. So point up if you think it's going to increase, point down if you think it's going to decrease, point sideways if you think there's going to change. What do we say? Very good. Have a smiley face if you're pointing. This one, once again, they should hopefully once again feel logical. Right? Don't just like memorize it, but just think about it. This demo is very boring because I couldn't think of anything better. What would I do to show this? Load more into the balloon, right? I can't think of anything more exciting, but that's what shows the point. So,
Yeah.
so what are the two variables we're focused on now?
Moles and volume.
Good. So this is a moles and volume. So we call this a direct or indirect? Indirect. No, sorry, direct. Because as one goes up, the other goes up. Right?
So is the other one indirect?
So indirect is when they're the opposite, meaning as one goes down, the other goes up. So this one, our equation would be
So,
V1
volume versus
over
pressure.
N1 equals V2
Volume versus
over
pressure is
N2.
indirect. And the other two.
Okay. Alright, questions on the visualizing side of it before we try a math problem now?
I don't like math.
Sucks.
Should've.
No. Maybe
I
one
signed
day
up for
you'll
AP
come
Chem
to
for
the
chemistry, not
right
math.
side of things and realize math is
What?
I said maybe one day you'll realize how awesome math is.
Well, like, I don't like long math problems.
Long ones?
Okay, I prefer hard math problems that are like shorter than long math problems that are easy. Why would that? I don't know, to screw everybody over? To figure out the triangles? To figure out the triangles?
You want to go into aerospace. That's
Shut up. There's a reason why I'm taking AP Chem.
Alright, so in this problem, key thing to recognize is we do multiple types of problems. Because sometimes, like, in the moment, a problem will make sense. But then all of a sudden, when you're doing a homework assignment or a test and all the different problems are scrambled, it can be confusing of, like, which method do I use of these similar types of ideas? So we should identify, first off, how this is different from the problems we did last time. So the problem says we have an inflated balloon. It has a volume of 6 liters while it's at sea level, which is 1 ATM. Okay, we allow the balloon to go up into the air until it gets to an altitude of 0.45 ATM. Okay, as this balloon is rising up into the air, the temperature drops from 22 degrees Celsius to 21 degrees Celsius. Our goal is to calculate the volume of the balloon at its final temperature. Now, once again, I'm always in the habit of circling my goal. Right, that helps me keep my target in sight, or like where am I trying to get to in the end so I don't get lost. Okay? Now can anyone see what is different about the wording of this problem from the problems we did last time? You know someone? Good, it's like there's a comparison. Before, it just said, here's the pressure, here's the volume, here's the temperature, what are the moles? Right? This is now a comparison. So in this case, we're still going to use this equation, but we're going to rearrange it so we can have that comparison idea. So what are the 3 variables we're comparing?
Volume, pressure.
Good. So we want pressure, we want volume, and we want temperature. So my equation for this problem is going to be P1 V1 over T1 should equal P2 over V2 under T2 over T2. Once again, this orange equation is on your formula sheet. This one is not. You need to understand how to derive from here to here. Questions on how I got there? Yeah. Oh yeah, you need one?
What? How did I have one? What's 6 divided by 2?
Okay, so now the matter is of just finding what we need and then plugging it in and making sure the units cancel each other out. Okay, so which of these variables is my end goal? Good, V1 or V2? So the goal is to find V2 because it's the volume at the final temperature. Some students like to put PIPF if you want to think initial final. If you like it better that way, either way works. Okay, so I'm going to rearrange this equation. So V2 is all by itself because that's what I'm trying to find. So mathematically speaking, the first step I would do is move T2 to the other side by timesing by it, right? Just like algebra here. Okay, so I'm going to times both sides by T2. Okay, I'm going to write this in various steps so you can see like the process of how we get there. So my new equation I'm going to write here in red. Okay, so since it's timesing, the T2 goes on top. So it's P1, V1, T2 over T1 is going to equal, oops, sorry, don't. Oh yeah, sorry, P2 and V2. So I went from here to here by timesing by T2. Now, once again, V2 is the goal, so how do I get rid of P2?
Divide by P.
Okay, so now I'm gonna divide by P2,
Heck.
which since you're dividing it, it's gonna put it on the bottom over here. Okay, so my new equation, okay, for V2 is gonna be that V2 is gonna equal P1 V1 T2 over P2 P1. A lot of letters here. Questions on any of my algebra steps there? If by chance, I try to explain some math as I'm doing it, but I also have the assumption that there's certain math skills you already have. If there's ever time though that you're like, I don't understand, let me know and I'm happy to like help you learn a math skill if you feel like you don't understand. Okay? I don't teach math, but I do have a math minor, so I. Okay. All right. So at this point now it's just plugging all the numbers in. Okay. So P1, go up to my equation.
1.
Was 1 ATM. If it helps, maybe draw an arrow, or if you want to write next to 1 ATM, hey, this is my P1, right? Okay. So P1 is 1 ATM. What was my initial volume?
6 liters.
6 liters. Okay. T2 is the final temperature.
252.
Good. So write some notes. So this one we do have to convert into Kelvin. So Kelvin is we take the number and add
It's a nerd draw.
273. Once again, that number's on your formula sheet. Okay, so 252. What do we get?
2? Oh, I think right.
Okay. Once again, if you want to draw, I'm just pulling things now mostly from the problem. The hardest work is getting the equation. Okay. All right, P2, what was my final pressure? Right there. 0.45 ATM. And my final temperature, or my initial temperature,
295.
same thing, gotta add 273. 295.
295. It's not.
Questions on where any of my numbers or things came from? Once again, if math ever feels magical, meaning like, where did that come from? Ask a question. It's not magical. It's cool, but math isn't magical. Yeah, here. So it's always just whatever Celsius is, you add 270.
So then there's less pressure.
Yeah. And that's on your formula sheet too. Yeah, good reminder. Yeah, Levi.
Oh yeah, that's true.
Yeah. Yeah, because the negative really
It's both of them act on it.
messes up the
Right.
so
But then
it's
it
like a
increases
negative
the volume.
Yeah, good question. Plug it in your calculator. If you do it right, you should get, I think it's 11.4.
Wait, why did you write down 6.02?
Try
that's right.
typing that in.
This is how these your liters looks like a 2, so I got really tripped up for a second.
Oh, it has a little hook at the top.
11 points.
I did too, but I still got the same number.
Well, yeah, because it's just a minimal
You
time.
get the right answer when we text it in.
That's because I just,
Why did you say big yet?
Wouldn't it just be 11?
Yeah, they gave us a really ugly number. I don't know who they were, but I was mad at them. Because 1 is only 1 sig big, so theoretically it could be
1 liter?
oh.
10. Because 10 only has 1 sig
Oh
big.
yeah, because I forget.
I would say on most AP questions they're going to give you a more like 1.0, 0, something like that. But theoretically,
What?
questions on this problem? 10 to 6. Yeah.
The smallest.
Now, I mentioned this before. Okay, so look up here, everybody.
That's how it works.
The benefits of putting units into a problem is it like checks your work for you. Because if you throw the units in there, in the end, they should all cancel away except for the unit I want. So ATM is on the top, there's an ATM on the bottom, there's a Kelvin on the bottom, there's a Kelvin on the top. And the only unit that isn't gone is the unit I don't want to be gone. So units are a great way to check your process. Okay? Now keep in mind with the FRQ section of the test, You must show some amount of work to receive credit. If you simply put an answer, they will give you 0 points on the FRQ. That's my guess, is they just assume you looked at your neighbor and wrote it down. So you have to show some amount of work. Okay? If anything, show what you're putting in your calculator. Like if you did it all in your head, but you're typing in your calculator, write down at least the equation you put in there. It doesn't have to be like, you don't have to show like, in math sometimes you have to like show the simplified steps, right? You don't do that. But you've got to show some sort of logic to your answer, otherwise they won't give you points, okay? Alright, questions on this? Okay, 2 other equations now that are actually focused just on the pressure side of things. Is this idea of a combination of gases and how pressure is influenced. So with this idea of pressure, pressure is an additive property, and it kind of makes sense why it is, but you should understand why the others are not. Okay, so first off, let's write this equation. These are both on your formula sheet, so we don't have to memorize them, just got to use them. So the pressure of a total container. Okay, so if in my balloon theoretically were a mixture of gases, and I wanted to know what the total pressure of the balloon was, it's always going to be equal to the individual pressures of everything inside. So whatever it's made up of is going to equal the total pressure. Right? So all the individual pressures will equal the total. Okay? Anybody know why though? Why would be, if I was dealing with temperature and I have all my individual gases, why is this property not true for temperature? Izzy? Good. And if they're all in the same room, right? So in this room right now, there's CO2, there's oxygen, there's nitrogen.
It's all happy.
Right? What's the temperature of everything in this room? Whatever the temperature of the room is, right? So it's not an individual additive thing of like some of the gas molecules are at like 20 degrees and some are at 50 degrees and they add up to the total. They just all equal the total. Does that make sense? How's my face, Caleb, for helping us out there too? Volume, why is volume not an additive property? A volume of gas, why can I not divide up the individual gases in this room? Alex?
They kind of all just occupy the same space, right? Because they're just going.
Right? It doesn't matter that there's oxygen, nitrogen, carbon dioxide in the room. It's not like they have their own volume. They all fill the entire volume. So it's not an additive thing. Even liquids with volume isn't perfectly additive. When you mix 2 different liquids together, sometimes the volume can be less. You can add 10 mils, and the total volume is 18 mils. When you mix them together because of how they interact with each other and they actually come closer. So volume is not an additive property, temperature is not an additive property, but pressure and moles are both additive things because they're related in that way. So Alex, did you have another question or comment?
Yeah, so if you have like a bigger molecule, does it move slower through the room and would technically have like a slightly lower temperature, or is that just like...
Great question. How's my face for it? I'm not going to answer it. For 10 minutes, and then we'll actually talk about it today. But I want you to think about it, but we'll come back to that today. Okay? Alright, the other equation we have is just like this kind of in reverse of like if I want to find just an individual pressure. So if I want to find what is the pressure of A, okay, the 2 things we need to know are this. We need to know what the total pressure is. Then, if we also know the amount of the particles, meaning the mole fraction, so the mole fraction is a Greek symbol, as many of our symbols are. It's called chi, is its name. It's a fancy X. So it's not X, it's chi, C-H-I.
It's the guy from the
You add a little fancy curve at the top, okay? At least that's how I draw it by hand. You look it up, it looks equal. Okay, so this, what chi equals, is chi is the ratio of how much A is there compared to the total moles. So in my room, if there's 100 moles of gas, how many moles of them are A? Right? If there's 10, then my ratio would be 10 out of 100. Right? So it's just comparing how many are there total versus the part I'm focused on. Okay? Once again, all these equations are on your formula sheet, even like this one is too. Okay, so we just need to know how to use it. So let's try a problem together, and then I'll have you try one with your table buddy. So in this problem it says we have a mixture of several gases for this experiment. We got oxygen, nitrogen, carbon dioxide, and water. Okay, the total pressure is 1.2. We want to find what is the partial pressure of CO2. So once again, circle the goal. Know what your target is so you don't miss. Okay, so right away, if the problem is focused on a partial pressure, that tells me I'm most likely going to be using the partial pressure equation. Or in a sense, I'm not even going to put A anymore, I'm going to put CO2. So we want to find just the pressure of CO2. So our equation says to find the partial pressure of CO2, we need to do the pressure of the total pressure of the system. And then we're going to multiply it by the ratio of CO2. So this is just equation we wrote down before, I just wrote it in terms of CO2. So the problem told me what was the total pressure of our system? Okay, so right here, so 1.20 ATMs. Okay. The mole fraction for CO2 is going to be how much CO2 there is. So looking at all my numbers, how much CO2 do I have? 0.03. 0.030 moles of CO2. Over, what's the bottom part of this fraction?
0.4,
And how did you get that, Bryson?
because I added up the moles.
So we add up all the moles in the system. Alright, so we gotta add up O2, N2, CO2, and water. So if you add up all the individual moles, we get the total moles. You got 0.4? Anyone else do that? Yeah, I was like, it sounds right from what I remember last period, but. Okay, so once again, this was just adding up lower numbers. 0.06 plus 0.3 plus 0.03 plus 0.0. So that's how we get the total. Okay, plug it into your calculator and we get a partial pressure of 0.09.
0.09.
What would the unit?
ATM. Automatic teller machines.
It's a pressure.
I feel a lot of pressure when I'm at the ATM.
That is so funny. Like,
Try to remember your pin
I
number.
never made that connection in my brain.
Really? Are you kidding me?
I just always think pressure.
What?
I've been doing chemistry too long. Like the ATM.
When's the last time you used an ATM?
I don't know if I've ever used one.
Well, there you go. There you go.
I've never used mine.
I used an ATM in the last.
I can't
We're like, I don't like it. Cash is an old person name. You know, cash actually is a real money. And if your bank account money doesn't.
Wait, questions on this problem? Alright, try this one. So here's how I want you to do it. Ready? So, first step, take a minute and look at it by yourself. I'll time you. So 1 minute, no talking, see what you do on your own. After the minute's up, then you can talk as a table group. By the end, you need to have one answer as a table, and you're going to write it on your board for me. So you either all get the smiley or you all don't. So you got to be united in what you think the answer is. Okay, but 1 minute, no talking. See what you can figure out on your own, and then I'll let you talk to your group, okay?
Okay.
Yeah, ALCL little. As you're working, I'll give you a hint that the picture is there for a reason. You can't solve this problem without using that picture. minute is up. If you want to keep working on your own, you can, but if you'd like to start talking to your neighbors, go for it.
I'm finding the mold right now. How many molds is aluminum?
I have no
Stupid thing.
We're gonna have to use molds.
Well, I'm thinking, oh, sorry. I'm thinking chlorine. CL3 is 160. How many, where's aluminum on this thing?
Because what do moles measure? What's a mole unit?
Where's aluminum on this thing?
It's like a counting number.
This is all these, I can't find aluminum. Oh, it's up there, you stinker.
So pressure in one specific area of the thing could change. If you're looking at the whole entire container.
Oh yeah, this is
But I don't think we need to.
Once again, as a table, once everyone agrees on an answer, put it on your boogie board.
So what are we trying to find?
Oh, I'm just trying to break it down.
Yeah. Are you breaking it down?
Because I was trying to find.
Then we need pressure.
Yeah, you're not using that number until then.
How many moles of AlC3 versus how many yes are in the actual? Guys, we're gonna have to like write with the eraser. What did you guys get? I got 15.40. That's just which one is the eraser? Is this the eraser? Yeah. Can't really work. Do you hold it down?
So the 7 and the 10 don't count as sig figs because they're a true counting number. So your sig figs would be dependent upon the 22.1. Yeah.
No, we don't want to rise. I mean, you can.
If you don't have the courage to erase your words.
We might have to.
It's actually one of my favorite exercises when I see a student who's filled it in through 7.
But the thing is, we didn't fill it in completely.
Oh, with your hands.
Oh wait, it still is there.
But like, it's just so this
Keep working hard at this video. I'm gonna get and you're thinking, again, if you're not using the picture,
Base is wrong. You can see it. It's there. Whoa!
Just stick with that.
but the problem is, you need what are the one value. So what did you
We have to do it for the good of humanity. 3, 2, 1.
Does that give you a ratio? That's not pretty simple. What's the ratio? I feel like I've had so what's the top number? What did should it represent? Closer. Not 3 to 10. What's the one you're trying to find?
That's solubility.
So how many ALC are
I started 3.4 after.
Isn't this the one that we?
Hot data now.
No, it's
Ephraim, take off your glasses.
it's never happened. It like
Get by your eyes.
it definitely
Beautiful.
it's like not a big deal.
You'll get a whole map. But in order to solve the structural pressure, that's what you're right? What do I need?
Even though I recommend for
We need equals in our T's, so we can keep it nice.
Hey, that's inappropriate.
So, how much do you
Shut up. I hope you jump on I can call your mom. Great job.
You just erased our answer.
I guess maybe you could get there. Maybe you could get there with your mom. Definitely not Did we decide yet? Put a combined answer on there for me.
15.5, right?
Oh yeah. No, because I was like,
Why'd you say
stop it, Ephraim Brooks. I will tell your mother. I can find her. Your mother helps everything, dog.
what is the definition of
I will run, I will
of that pH right? If I have a mole of ALCO.
The only stuff that was just apps.
This counts as
Really, I actually think it's more if I run on my
Does that make sense?
like,
How many total moles are there?
like if I like to
There,
go on my
fix it.
run.
Text you, I text you, and then take your
Burning to the lab.
No, it's wrong.
You know, I have to go ready.
Good job, girls.
I can't rate.
It'd be like,
Not the vibe. Not the what, how I hate this.
I can't even do it. I really
Great, I think I made the rounds and checked everybody. You should have 15.5 ATM with rounding for sig figs, but if you got 15.47 is what it calculated gives you. Go ahead and answer the case. Questions on this? Now, this was our first exposure to what is called a particulate view of a system. Okay, the AP test loves to bring in pictures like this. So we'll get more familiar go, but let's point out a few. What are maybe some like, because I've never introduced you to one of these before, what are some things we learned that we can take away? Like when you look at this, anyone willing to share maybe some takeaways they got that they like, oh, I didn't realize that? Yeah, Porter.
If they provide it, or like, if they provide it, it's probably useful in some way.
Yes, good. How was my page that, right? Now there can be data that isn't useful, right? Because I gave you liters and temperature. Now this does come from an FRQ question that had multiple parts, so those may have come in later. I don't know. I can't remember the question. But if they give you a picture, there's a reason for it. They may give random data, but they don't give like random pictures without a reason. So good. Any other observations about interpreting these pictures or things? Kenzie?
So for this problem specifically, I kind of oversaw it and saw that like the bigger chunks were the same as two of the small ones.
Yes.
Look them up.
You did what this table did. But why is that not what we do?
Because we're looking at the whole.
Yeah.
So like the bond.
Right? This counts as a mole. Okay? This is another great example that moles is not an additive thing. When you balance an equation, you can have 1 mole plus 1 mole still equals 1 mole. 1 plus 1 equals 1 when it comes to moles, because it's about things becoming something bigger, but that bigger thing still counts as 1. To give you an example of a simple equation of where that's true, if I have molecule A, that counts as 1 mole. Combining with molecule B, that's 1 mole. But if they turn into molecule AB, it's still just 1 mole. This doesn't count as 2 moles because it's made of 2 pieces. It's counted as a group substance. Okay? Questions on that? Okay. The next thing we're going to look at, and we'll get to Alex's question here, but we got to take a little, not quite sidestep, but we need to make sure we understand something. Oh, my we're going to get to more of now, it's just more the conceptual side of it. Okay? Let me switch my PowerPoint here. So this first page here is known as the kinetic molecular theory. We've actually already talked about a lot of these properties of gases. This is just giving it to you in a place you can reference it. You don't, once again, don't memorize this list. Okay? The idea is just, can you understand how a gas behaves? Right? So if a problem ever talks about, hey, justify your answer in terms of the kinetic molecular theory, they're not saying, oh, you know, like quote number 2. They're just saying, think at the molecular levels, right? So the kinetic molecular theory is just understanding at the molecular level what gases do and what they don't do, right? So as we know, gases always are in constant random motion, right? The gas molecules are always moving around. Okay, number 2 is that the combined volume of the molecules is like 0. And you can see that with the balloon, right? What happened to the volume of the balloon when we put it in liquid nitrogen? It was like almost 0. That's how much empty space is in the balloon. Is that when the molecules actually come together, they take up no space whatsoever. Okay? Number 3, right? IMFs don't really matter when it comes to gases. They're just moving too much. So we don't think about hydrogen bonding or dipole forces when they're a gas. Okay? Energy can be transferred, so it's like bumper cars, right? As the molecules are flying around the room, if a fast one hits a slower one, they can transfer the energy as it goes around, but that average is maintained. Okay, same thing as they hit the walls of the container. Okay, and then the last one is that the average kinetic energy of the molecules is proportionate to the temperature. So whenever you read a question that talks about temperature, your brain should think about movement. And then also in reverse. If a problem is talking about the average kinetic energy of the molecules, your brain should think this has something to do with temperature because they're one and the same. Now, keyword here is the same average, right? So in this room, as Alex brought up, there's lots of different gases. Some of them are lighter and some of them are heavier. Their average will be the same, but that doesn't mean they have the same distribution to get there. Okay, and that's what we're going to look at next is a distribution graph, okay? Any questions on these properties? Hopefully, once again, it's just giving me that visual of at the molecular level. And then once again, pressure is about collisions, right? So any question that deals with pressure, you're thinking about collisions with the walls, how hard and how often they're hitting. Okay, how hard and how often. So if they hit more, pressure will go up, or if they hit harder, then pressure also goes up. Okay, so there's two things that can influence pressure. Okay, everyone good there? All right, take a look on your table, and there should be two of these little laminated graphs. Give one to each side of the table. Okay? Okay, and then there should be scattered about 2 expo markers. If you can't find them, look in the boxes. They might still be in there. Grab an expo marker. We're going to do some drawing on this graph. Okay? Oh, okay, everyone have their supplies. Anyone missing something? Oh, your expo marker. Which I don't even know because it was a brand new.
So with more speed, you have more
Maybe I should test it. Maybe they just thought it was dead. Okay, ready? Okay, so we're going to be looking at what are known as distribution graphs. Okay, so we're going to have a little side lesson in, I guess you could call it statistics. If you've never taken a statistics class before, which I'm guessing most haven't, because if you were to take it, take it typically until your senior year, then it's still like not everyone takes it. This also will be familiar if you've taken, I'm not saying you've had to, so if you haven't, don't be like, okay, but if you've taken calculus, there's a connection to that as well when you learn about area under a curve. Or if you're in calculus now, when you learn that, you can be like, oh, this is what we're talking about. Okay? So a distribution graph, they're a little different in how you have to look at them. So you need to understand it, otherwise it can be very confusing. Okay? So the way this distribution graph is created, okay, so first off, x-axis and y-axis, pay attention to. So the y-axis represents the number of molecules. Okay? The x-axis is the speed of the molecules. The way this graph is created is that it is like an infinite number of bar graphs side by side, and after the bar graphs are there, they create this curve. Wow. Okay, I'm going to show you a simulation that kind of gives you that visual. Okay, so let me pull up my first simulation here. Okay. Okay, so notice, so here's our molecules moving around. Okay, and then here's the distribution graph.
Bro, what?
So notice the orange line. Can you guys see that orange line from the back?
Yeah.
Okay, so that's the line you see, but it's created through the process of, hey, there are this many molecules that are traveling at a speed of 2. There are this many molecules traveling at a speed of 1.5. And there's only this many molecules traveling at this one, and obviously 0 and 0 will always match, because there's going to be 0 molecules that aren't moving, because they're always going to be moving. Okay?
Look at them.
All right. Everyone kind of see how it is? So when you look at a distribution graph, you should visualize that the entire shaded area under the curve represents the total number of molecules in the container. Right, so if I shade that whole area in, that's like all the molecules at all their different speeds being shown. Okay, any questions right now? Okay, let me show you a second simulation here. Okay. Okay, so let me do this really quick. Start. Okay, so molecules are moving around. Right now I'm at 0, 0, so they're all gray. Okay? Notice as I drag this over to highlight an area. Okay? So this shaded in section is representing all those red molecules. And would you describe them as fast or slow? Slow. Slow, right? Which is because they're on the speed side of being slower. As I continue to highlight more, it will then pick up, so now there's this many, all of these represent that whole shaded in area of the molecules. Right? So even though there's an average in the room, you can have some molecules going quite slow and other molecules that are going quite fast. The average falls right here. This red line, that's the average speed, which is based on the temperature. Okay? Questions on our distribution graph? Okay, so here's my question to you that you're going to do with your table buddy on your little graph that I have for you. Okay? if that graph represents oxygen at room temperature, how is the graph going to change if I heat up the room? Draw me a new graph on top of that graph to show me how the graph will change. Talk to your table buddy, and then draw me a picture, okay?
Here's the new update.
Energy's increased So yeah, since there's more energy, more of them are moving at a faster rate.
So it's just a little.
I got my 3 credits. I'm good at that. Actually, I technically have 4 credits.
So it's
Draw me a new graph.
oh no, it's
Physics, calculus.
There's 3 smiley faces up for grabs with this one graph. So there's 3 different things I'm looking for.
Do you like my smile?
He looks very happy today. Okay.
Quick!
Because there's still 0.
What is she looking
just make sure it goes.
You are all mostly united. Okay. Show me your answers. I kind of looked, but show me your names.
It's faster.
Okay, so 3 smiley faces here. So number 1, you can have a smiley face if you kept your starting line at 0, 0. Because it always stays at 0, 0 even when temperature goes up. Okay? Alright, second smiley face, which you all learned, is for shifting the graph to a higher speed because temperature means faster molecules. So I have a second smiley face, everybody, because everybody got that. The third one, though, I only saw one that deserves this one.
Do you have to make it smaller?
So here's the catch. Zach, you asked, I don't know if you remember, do you remember you asked a question about the number of molecules? Everyone listen to this real quick, okay?
I was like saying it would just have the same amount of molecules as before because it's still the same like amount of oxygen.
Okay, so if I heat a substance up, is that going to change how many molecules there are? No, right? It's just they're going faster. So if you were to shade in the area of your new graph, is it going to be equivalent to the shaded area of the original? It's impossible with how you all drew it. Watch what happens. So here's my original. It's going to draw a second graph here. So as I heat it up, if they're going to move faster, the distribution must change. Because you can't just because your graph gets bigger if you keep it at the same time. Does that make sense? You guys were close because you made yours actually a little smaller than.
We did that too.
Oh, you did too? Oh, okay. Just a tiny bit. But if it was purposeful in it, then yes, you can have it. I didn't know if yours was purposeful or just Okay. Does that make sense though? I visualize everybody, give your tips here, still like 2 minutes left. If it helps, and I was going to do this, but I didn't know if it'd be helpful or not, but I visualize this line as like a string. And so if it's going to get hotter, you pull the string out, but what the string's going to... So in reverse, what would the graph look like if it were to get colder? Draw me a third one real quick. What? Yeah, first mine.
Colder?
You can leave your other one on there.
So hard.
Yeah. Molecules. We went into the negatives.
Okay, Okay, ready?
Let's see it.
Awesome.
So you drew it farther over, but it should be higher up now because like you don't have the same area as you did before. Okay? Questions on this idea of distribution graphs? Okay, let's just put in the notes what you just said. Okay? So with this idea of a distribution, right, we're at the same temperature, the average will be the same, but the distribution can be different. If temperature increases, then it's going to spread out accordingly. Okay, because that average is going to go up, but even at a hot temperature, there's still a chance of some molecules going quite slow, right? But your overall average will have gone faster. And then our next graph we'll look at, we'll finally address Alex's question with the idea of different masses, where yes, if they have different masses, their distributions will look different. Is everyone good on this one? Okay, so with this one, this is showing different molecules, so not different temperatures, right? But helium is really light and small, so it's going to have a much bigger distribution because it can go really fast, versus heavier things would have a much slower, less spread out distribution. Okay, so there's a factor of temperature can have different distributions, but also sizes of molecules can have different distributions. But if they're in the same room, the average of their distributions would be the same. Even though some helium can be going really fast, the average would be the same nonetheless. Okay?
Awesome.
All right, we will move on.
The heavier it gets, the slower, like the less bearing.
Oh, we get out. Yes, my watch said 07 using 6 minutes left. I know it's not.
Yeah, it is.
My birthday is 12/16 right now. You're welcome. Your face is You're racist now.
Yeah.
You love driving race cars. You like driving race. I'm a professional racer. What are you gonna ask about? Oh yeah, it's because it's obviously it's ionic.
So think if you have
I would say don't worry about it, but you can still ask
you
her.
have volume,
Don't worry about it.
you have temperature, always have R.
This is all Bezo.
So that's how you can find.
Can you pass me a marker?
It's just the R constant.
There's
value,
no marker on the
it's just
table.
that set number
Oh,
or
It's kind of small.
Define shit
Oh,
though.
82067.
Can you
So
pass
if
me
you
one?
have, so since you have these, you can find that one. Just by plugging in. And then just plug in the volume they gave you, temperature, and then the total moles for the total pressure. So that would give you the value of the total pressure. Yes, yes, so that's the case. All these problems can look different, but in the end, I ended up figuring it out. Did I give you a formula sheet last time?
Yeah.
So yeah, so what I would do is like on this one in particular, right, is just, so it's just this section. So the only three options of equations are these three. It's gonna be one of those three that you're gonna use.
Next week. Monday? Monday?
Oh man.
So when will we see each other Monday? Oh man.
Just copy this down.
It could happen.
Or just any other time. See ya, Alex.
What is these forces that we're talking
So do you remember our different type of IMFs that we have? So what are the three different kinds?
There's the solubility, the water, the pressure.
So those are, I think it's gonna be
There's the
different.
boiling point.
So those are the applications. The forces themselves were the London